Okay, Chapter 6, 6.1, Antiderivatives and Slope Fields, Part 3. Your objectives for this lesson are to solve initial value problems, sketch a slope field, and evaluate an indefinite integral. We have two examples that we're going to look at during this last video. So example 7. A right cylindrical tank with radius 5 feet and height 16 feet that was initially full of water is being drained at the rate of 0.5 times the square root of x feet cubed per minute. Find a formula for the depth and the amount of water in the tank at any time t. How long will it take the tank to empty? And this problem is using Torricelli's law, which says that if you drain a tank, like this one in this problem, the rate at which the water runs out is a constant times the square root of the water's depth, x. So you can see here, square root of the water's depth, x, times a constant. So here our constant is 0.5 or 1/2 x. What I want to do here first is just sketch a picture of what we are looking at. Drawing a picture is really never a bad idea. So a right cylindrical tank means my sides are going straight up and down, like so. Okay. And I have my water in here, and my height at any time, well, some random time, is x. I know that the volume of a right cylinder is V equals pi r squared h. So area of a circle times the height. So for this tank here, I know that my radius is 5, and it's always going to be 5. Tells me that radius is 5. So pi 5 squared h, or not h, sorry. Our height at our time is x. So volume is 25 pi x. So this is the volume of water in the tank. Okay. So our differential equation then from this will be dv dt, so we're differentiating both sides with respect to time. 25 pi will stay the same, and then the derivative of x is dx dt. And really, since this is draining, this should be negative. So, because my water is draining out of the tank. Okay, and I know from my problem that the water is being drained at a rate of 0.5 square root of x feet cubed per minute. This feet cubed, again, if you have trouble with this is your tip-off that we're talking about a volume. So do pay attention to your units. That is dv dt. So I'm going to put that in right here. 0.5 square root of x equals negative 25 pi dx dt. Awesome. Okay, and what do I want to find again? I want to know how long it's going to take to empty the tank. And I'm going to go ahead and get my dx dt by itself, since that will be helpful to me. So I'm going to divide both sides by negative 25 pi. And these cancel. So my dx dt left over here and, well, 0.5 divided by 25 is 1 over 50. So this is negative square root x over 50 pi. Okay, and I know my initial condition is that x of 0 is 16. So at time 0, we have 16 feet height. Basically, when the tank is full, the water height is 16 feet. Or, is it feet? Yes, 16 feet. Okay. Next, we're going to try to solve this equation. So, solve. And I'm going to do some more moving. I want to put this x on the other side of the equation so that I can integrate. Okay, so this is negative x to the 1/2 times, or not times, divided by 50 pi equals dx dt. And I'm going to divide by x to the 1/2, which is the same as multiplying by x to the negative 1/2. So I have negative 1 over 50 pi equals x to the negative 1/2 dx dt. Alright. Next we're going to integrate both sides. And when I'm integrating this over here, I can move, it's one of our rules, my negative to the outside there. Over, oh gosh, over here, I need to add in my variable of integration. So deriving with respect to t, so we're integrating with respect to t also. Over here, those are going to go away. But not over here. Here they will stay. Okay. So to actually integrate, right here, I know I'm going to add 1, so like that, and divide by my new exponent. So divide by 1/2 means multiply by 2. And this equals, well, what happens when I integrate a constant? I get, well, a t thrown in there really. So negative t over 50 pi plus c. And now we need to plug in our initial condition. So remember, x of 0 equals 16. We're trying to figure out what c is. So we're going to plug in a 0 for t and a 16 for x. Okay, and since we have a 0 divided by a constant, that just goes away. So I have a c left on the left, and 16 to the 1/2 square root of 16 is 4. So 2 times 4 is 8. C is 8. But we're not done yet because the problem didn't say what is C. It did not even mention C to us. What we need to do, where did that go? Under pointer. Oh gosh, it's a lot of work. We're going to take this problem right here, not problem, this line, and plug in our c to that line. So since c is 8, 2x to the 1/2 equals -1 over 50 pi times t plus 8. Now we do have a 2 here, so we can divide everything by 2. And we get, 8 divided by 2 is 4, minus 1 over 100 pi times t. Okay, you could also put the t up top here. Okay, so the formulas that we need then are this one, and really what I'm going to do is I'm going to square both sides to undo that 1/2 and get this. So squaring both sides, and we need our volume formula from before. Okay. And since this is what x is, I'm going to plug that in right now. So really volume is 25 pi times 4 minus t over 100 pi, quantity squared. Okay. So at any time t, the water in the tank is this deep, so 4 minus t divided by 100 pi, all squared, and the amount of water in the tank is what I have for volume right here, feet cubed. At t equals 0, we already established that our height was 16 feet. We could also plug in those numbers for our volume. So let's do that right now. T equals 0. Our volume is 25 pi times 4 minus 0 over 100 pi squared. This part goes away, so this is just times 4. So this is, oh gosh, 4, this is 16. 16 times 25 is 400 pi feet cubed at t equals 0. Okay, and the tank will empty, so volume is 0. Well, the volume will equal 0 when this thing here is all equal to 0. So basically, 4 minus t over 100 pi is equal to 0 when 4 equals t over 100 pi. Can multiply these both by 100 pi. So when t is 400 pi minutes, then the tank will be completely drained. And if we convert this into time that you understand, instead of 400 pi minutes, this is about 21 hours. Okay, that's a long time to wait for the tank to drain. Let's go on to the next problem. Okay, example 8. A heavy projectile is fired up, straight up from a platform 3 meters above the ground with an initial velocity of 160 meters per second. Assume that the only force affecting the projectile during its flight is from gravity. which produces a downward acceleration of 9.8 meters per second squared. If t equals 0 when the projectile is fired, find a formula for the projectile's velocity as a function of time t and height above the ground as a function of time t. Alright, so just like last time, I'm going to start you off by drawing a little picture. This picture will not be quite as pretty as the last one, so I apologize in advance for that. So we have our platform. Label it platform so you know that. And that is 3 meters above the ground. Yes. This is 0. Height of 0. So whatever this is, it's getting shot straight up into the air. You know, it's going to curve back down. So here is our projectile. And this is the ground. Okay, so I want S to equal the projectile's height above the ground at time t. That's pretty standard. We've been using S for position. And S is going to be a twice differentiable function where velocity is the first derivative of S and acceleration is the derivative of velocity, making it the second derivative of S. Okay. So gravity acts in the direction of S decreasing. In other words, when S is getting smaller because your projectile is falling down to the ground, the height is decreasing. That's because gravity is pushing it downward. So our differential equation, is the acceleration, or our second derivative, equals negative 9.8. Okay? And again, that's because gravity's pushing our projectile towards the ground. Our initial conditions. We know that the initial velocity at time 0 is 160. So initial velocity of 160 meters per second. And we know that at time 0, we are at, or the projectile is at, 3 meters above the ground. Okay, so the first thing we want to do, part A, is find the velocity as a function of time t. So if we're looking for velocity, we're looking for ds dt. Find ds dt. Okay. And we're going to do this by integrating that second derivative. Okay, so the integral of d squared s dt is equal to the integral of what that is equal to, so negative 9.8. These go away, so I'm left with the integral of that second derivative is just ds dt. Oh, this is squared. And this gives me negative 9.8 t plus c. Okay, but that doesn't really tell me anything. I need to find c. So we're going to apply our first initial condition. So I'm going to plug in a 0 for t and 160 for my derivative. That goes away, so we're left with c is 160. So our velocity, which is ds dt, equals negative 9.8 t plus 160. Okay, found the velocity. Part A is done. Part B, we need to find the height as a function of time t. So we're looking for s. Okay. And again, we're going to integrate. This time we're going to integrate what we just found. Okay. And we get s equals, I need to move this up a power, so I'm going to divide negative 9.8 by 2, and I get negative 4.9 plus 160t plus c. But again, you know that we can't just leave that c there. And really I should label this c2 since I've already used up c1 here. So we're going to apply our other initial condition that we had. So s of 0 equals 3. So when t is 0, meaning we have to plug in a 0 for t, this is 3. So cancels, cancels, and just like that, c sub 2 equals 3. So we have s equals negative 4.9 t squared plus 160t plus 3. And that is the end of that problem, and I believe of this video. Yes, it is.